We will be discussing Phys2212 Lab 1, Charged Tapes. So to begin, this lab is intended to perform three objectives. First, we want to investigate the charge that accumulates on pieces of tape. Secondly, we want to determine the amount of charge on that tape. And third, we want to determine how many electrons were involved in that charging process. So firstly, some fundamental principles that we will need. Newton's third law describes that for every action, there is an equal and opposite reaction. This notation here describes that. Second, Coulomb's law describes the force that exists between two charged objects, and this equation is explained here. Thirdly, the law of universal gravitation describes how the gravitational force interacts between two objects. In our case, it will be a piece of tape and the Earth. A quick preview of the results. The charge on each piece of tape was determined to be 4.67 times 10 to the minus 10 coulombs, and the number of electrons lost to produce this charge was 2.9 times 10 to the 9 electrons. We know electrons were lost because each tape was determined to have a positive charge, and since we are losing negatively charged electrons, we thus pick up a positive charge. So here are the details of the experimental system. Here are the parameters of the tape that we used. This describes how we produced charged tapes. We stuck down a base tape, we put another piece of tape over it and ripped it off quickly, and handled it as little as possible. The U-tape became charged. In order to determine the charge on the tape, we set up the apparatus shown to the right. We held both tape A and B were charged, and we held charged tape A under charged tape B until repulsion was observed. The displacement of tape B from its original position was thus recorded, and then this was used to compute the charge on the tape. The surroundings of our system include our hands, the table, and really everything else other than the two pieces of tape. So, how do we know the magnitude of the force on the tape? Well, in order for tape B, the top tape, to be displaced, the electric force on tape A must be greater than or equal to the force of gravity. We compute the force of gravity on tape B by the following computation, since we know the mass of tape B, and it was determined to be 0.00196 newtons. So E must be greater than or equal to this value. We observed repulsion between the tapes when the distance between them was 0.001 meters. Using this equation here for the force of the electric field, we computed that the charge on the piece of tape on tape A must have been 4.67 times 10 to the minus 10 coulomb. Now, we want to know how many electrons were involved in this process. We know that the charge of tape is this value here, so we can divide this charge by the magnitude of the charge of an electron to determine how many electrons were lost from the tape. And it comes out to 2.9 times 10 to the 9 electrons. How many atoms gave up an electron? We know the area of the tape, and we know the area of an atom. So thus we can determine how many atoms were on the tape's surface. And therefore we can divide this value by the number of electrons lost to get this ratio of atoms to electrons lost. What this means is that there were 1.1 times 10 to the 9th atoms per every electron lost. In other words, the vast majority of atoms did not lose an electron, as expected. So, we performed a computational model of this situation, and the computational model concluded the same charge on the piece of tape at 4.6 times 10 to the minus 10 coulomb, as well as the same number of electrons lost. If you are interested, here is the code. The important parts here are computing the charge on the tape as well as the force of gravity. So let's cover some assumptions and errors in this lab. First, we assume that air resistance is negligible and friction. Secondly, we assume that each tape can be modeled as a point charge. And third, each tape has an identical charge, which is evenly distributed along the tape. This introduces some errors because obviously, tape is not a point charge. Secondly, tape is heavily subject to air resistance since it is so light with such a high surface area. And thirdly, charge can easily bleed off of tapes upon handling. So therefore, this means that the tapes will not be evenly charged. So now let's cover some hypotheticals. What if electrons had positive charge and protons had negative charge? What would change about my observations? Actually, nothing would. We would still observe repulsion between the tapes. They would both be negatively charged instead, but like charges would still repel like charges, so we would see repulsion. Now, why is it important to handle the charged tapes as little as possible? This is because our bodies and other objects are able to neutralize all or some of the charge on the tapes upon contact. Therefore, we would no longer see the desired electrical effects that require charged objects. I mean, if the tapes were neutral, no repulsion would be observed.